W14 by 38 column is made of A36 steel and is fixed at the base. If subject to an axial load of 15 kip, determine the factor of safety with respect to buckling. And there is all the stats for a W14 by 38 beam, 11.2 inch to the squared area, 385 inches to the fourth, and I-wise 26.7 inches to the fourth. And it's an A36 beam, so we can look up and find that our modulus of elasticity of the beam is 29,000 KSI, and my yield strength is 36,000 KSI. Now, what we want to take a look at is what's the factor of safety in respect to the beam. Now, remember, factor of safety is something that we brought up before, and so factor of safety is all talking about what the ultimate stress over the allowable is, but that can go to anything. We can sit there and look at the ultimate load versus the allowable load, or in this case, what we'll look at is the critical load over the actual load itself. And so if I want to calculate out the factor of safety for this, if I know what my load is, which is 15 kip, I'm going to calculate out what my critical load is. Now, this problem is a little bit different than the last one because we have fixed and free in both ends. And that's important because this is one of the cases where we're not going to have to calculate out both the x and the y direction. Because since we know that we're going to have the exact same the exact same effective length for this, we should be able to just immediately go that it's going to buckle in the y direction before it's going to buckle in the x. Now, I know I've said in previous problems you need to do all three, but in this case, since the effective lengths are just the same, just a statement showing that you understand it's going to buckle in the y direction before the x because they're both the same is really all we need. So in this case, then it's just we have to calculate out the factor of safety. And let's just write that again. So our factor of safety is going to be our critical load divided by our load. So we have to find out the critical load. And so I know the critical load is going to be in the y direction. So P crit is going to be pi squared EIY, because it's the least moment of inertia, KL squared. And once again, I just want to stress, the only reason that we don't have to calculate out both x and y is because since they have the same effective length, I know it's going to fail on the least moment of inertia. It'd be different if it was like the previous example, 13.3, where it's pinned in one direction. Then I'd want to see you work both out just to make sure that it's going to fall in this one. But this is, like I said, this one's easier because it is the least moment of inertia. So 29 e to the 6 psi, because when we convert from psi to ksi, 26.7 inches to the fourth. We're going to divide that by our column length, 2 times 20 feet. Multiply that by 12 inches divided by 1 foot. We're going to square that entire thing. And so we're going to calculate that our critical load is 33.17 kip. So 33,000 pounds. Now, I need to make sure this is valid. Because if it's not valid, if it's failing before the material, it has no factor of safety with buckling because it's going to fail before it hits there. How do we do that? Well, we calculate out our critical stress, just our critical load over our area, 33.17 kip, divided by the area, 11.2 inches to the fourth, and we're going to get 2.96 KSI. That is well below the 36,000 KSI. So this is definitely not going to buckle before the material. The material's not going to fail before the entire column buckles. The last thing we got to do then is, okay, well, our factor of safety is going to be 33.7, which is our critical load, 33.7 kip. And then we're going to divide that by 15 kip, given to us in the problem. And that will tell us that our factor of safety to buckling is 2.21.